You did a circular motion lab last week, uh, which is basically modeling the planetary motion. You had a stopper, which is modeled like a planet, and there's a string which is going through a PVC pipe with a bunch of washers hanging on the other side. The weight of them behaved like the attractive force between the sun and the planet, and you analyze that particular. You're trying to analyze that particular data and see what their possible errors are there. Now, your results will or you provide all well, you're providing results, provide all the values of the constants. For instance, in both cases, the mass of the stopper is a constant, and you are using the same type of string, and all those things are qualitative constants, but the mass of the um, stopper is a value which is a constant. And tablet independent and dependent variable, one pair of independent variables you had were one pair of variables you had was the independent variable was the radius and the dependent variable was the speed. In the other case, the independent variable was the tension and the dependent variable was the speed. Both cases, the dependent variable was the speed. Now you individually, depending upon what your pair of variables were, the scatter plot, determine qualitatively the relationship. Does it increase or decrease, or is it increasing at a decreasing rate, or do you find any kind of discrepancies or any information you want to outliers or something like that. Now, to analyze this data, yes, after doing this basic understanding of the results, to further analyze it, we need to pool the class data for each pair of variables. One is radius versus speed, the other is tension versus speed. The reason why we do this is to reduce the inferential distance and to get a better efficacy of the information what we have collected. This is also allowed because we pretty much kept the mass constant for all of them. For all of the data where the radius is varying, the load was kept the same. For all those which had the load is varying, we kept the radius to be the same. We are able to integrate this because of that. Now, plot the scatter plot for each pair of variables. Perform a power regression and provide the exponent and scale of the power regression. Now, write down the fit equation not in x and y, but the symbols of the variables, like this speed in terms of radius and speed in terms of the tension, and provide the R squared values in each particular case. Compare the exponents to the ones you expected from the dimensional analysis. Please watch the dimensional analysis video before you can comment on this one. Now, determine if the discrepancy is reasonable, considering the errors in this experiment. To determine that, we need to understand the nature of the errors. Now, let's quickly recall the types of errors you come across. Number one is the instrumental error. For this, you need to know the least measure that every measure can really, a change in measure it can measure, and also you need to know what is the least measurement you have made with that. The computation of the percentage error will depend upon these two things: the smallest change in value and the least value you measured with it. And you use the least value in order to overestimate the error. Because if you divide by a smaller number, then the error percentage will be higher, and that is the maximum error possible. Use your understanding to find the percentage error to calculate the error due to these instruments, and then you might have to add all those absolute values of the errors. Design error. This is where most of your error might lie, because you measure current to a millimeter, you current to a gram. So percentage errors in all of these things are not much, but in the design aspect of it, it will be way more. Like the string slipping up and down may even vary up to 1 centimeter, which is 10 times the error of what you would have seen in the case of instrumental error. So that is very important. There could be frictional forces which could significantly affect the amount of tension what you thought was there. These could be inherent to the method you used and cannot be avoided. For instance, the very method you used has a frictional force of the string between the string and the PVC pipe at the top, and it is not a single point, it's continuously rolling along the wall of it, so there are going to be errors because of that. Uh, and inherently, you cannot ever keep it at a horizontal plane. It is going to bend. It is going to be like a conical pendulum because there is going to be a weight of that particular stopper which you cannot compensate for unless otherwise there is an angle in the string. The component of the string is one that balances the weight. So that means the radius, what you thought was the length of the string, is not really the radius. The experimenter's inability to exactly follow the protocol due to the factors not considered. For instance, you want to keep the radius same by keeping the what do you call the pin or the marker from touching the pipe. Is also sliding down. It does go up and down. Then you're not supposed to add more force. You do add more, a little bit more punch to it so that it will keep rotating at the same radius. So these are certain things which you do in order to compensate for them, but how much are they adding sometimes is very difficult to estimate. Each of these will add to the percentage error, and they become more relevant when they exceed the corresponding instrument error. In this particular case, most of them will exceed the instrumental error in this case. The instrumental error, as we already talked about, you consider three variables and one constant. The values of each was measured using an instrument. List these instruments which contributed to the errors. Identify the least variation in the value of the instrument can measure, which is called the absolute error, and then identify the least measurement you made with that instrument and divide by that to overestimate the error. You know how to calculate the percentage error as the exponent of x times delta x over x times 100. Now add these absolute values to get the total. Now let's go to the design error. Now that is generally how the picture was. Now if you look at this clip, identify the source of your design errors. What are all the sources of your design error? Now look at this. Um, you what would you control as you expected? What could you not control as you expected? That's one thing you should focus on. How was the behavior of the movement of the object different from the way you expected it or wanted it to be? For instance, it was supposed to be in horizontal plane. It was not. So the radius was different, and you expected it to be at a specific length. But what happened was that small clip kept moving up and down, or sometimes you would have got a paper or something else kept moving up and down. Or you just made a mark and it's moving up and down. Was the radius you measured actually the radius? It is not, as you can see from the figure itself. Was it less or more, and why? You should most probably the actual radius is less than the length of the string which you thought was the radius. And was the radius constant in each trial? Again, we talked about this. It tends to slip up and down. It just keeps changing. Was anything done to compensate for the deviation of this behavior? You just moved it a little bit more with your hand in order to keep it where it was. Identify specifically how each would have affected the data. Like, I wanted to see if it would have made it faster, or would it have made it slower, or let's say, or say like that increase the radius, increase the tension. What did it do? That exactly you need to see that. Okay. Estimate the extent to which each would have affected the data. One of the things what we talked about is the slippage is about 1 centimeter. It looks very, very small, but the question is that is about 10 times the error in the measurement of the radius. And on the top of it, if even if the angle is, let us say, 80 degrees on the top, how much would have changed your radius? That also changes your situation. So, or if it did not change, if it does not affect much, why does it not affect much? Is the error uniform in all of them, so the trend looks the same? That's one more thing. uh, how significant are these? You compare that and you go on to do how can you do it better? Provide at least two specific ideas to improve the design of the experiment. State how it would improve the experiment. That's important. Just because saying something does not matter. Oh, I will find. Be specific about which design error would it have mitigated. Estimate to what extent. Don't randomly say that I would have measured the time better. Like, what do you mean by that? Better clock is not going to change anything much because you're already measuring 0.01 seconds, and but you're not. think about the fact that it is going around exactly when you're saying one circle is complete, and all those things. One complete circle is there, and three complete circles you measured there. Like, when do you know it is complete? And did you have any kind of system by which you say that it is complete? All those things, okay? And how can you improve that particular thing? Though you may suggest changing a specific measuring instrument, that's what I'm talking about. Just changing the measuring instrument to become more precise does not really count. Because in this experiment, people found out good relationships between V and R and V and tension with this level of rudimentary equipment, not with something phenomenally different kind of instruments, but with better design, but with being more careful about collecting the data and or possibly compensating for the possible errors, all of those things. It must improve the design and mitigate some uncontrollable factors of the design used. You need to be really creative for this. Like, how do you find a new or remodel the whole thing? Okay. You could provide new diagrams to explain.